Hey folks, welcome to day 15, Induction 2, Induction's Revenge. So, we'll be talking today about how you can control your induction hypothesis and why that's important. And then we'll also be doing some interesting programming with propositions as a lead up to day 16, which is going to be a big one. Okay, let's start with an example. I want to prove that the double function is injective. If I apply double to two different numbers and I get the same number out, then my two different numbers have to be the same, right? This hopefully is intuitive, right? If 2 times n equals 2 times m, then n should be equal to m. Okay. Now, keep in mind, this double is the one that does the double successor thing. So uh, now what's going to happen is this is going to go off the rails. Let's see what happens. Okay, so we're walking along innocently enough. We introduce everything. Okay, let n and m be given such that double n equals double m. Let's prove that n equals m by induction on n. Give ourselves an IH. Okay, great. So in the zero case, we say, okay, n equals 0, fine. We know that double 0 equals double m, and we need to show that m equals 0. We can do this easily enough by case analysis on m. So, okay, look, m is either 0 or successor of something. If m is 0, we're made, right? Isn't even necessary, and we just have 0 equals 0 immediately. Now, on the other hand, if m is the successor of some number m prime, well, the situation's a little different. Here, eq says double 0 equals double s of m prime. Now, you may or may not remember exactly how double is defined. A print command will do you nicely here if you don't remember. Um, but if I simplify, we can see what it does, and we say, wait a minute, wait. Double 0 equals double s of m prime. It means that 0 equals successor of something. That is not going to happen. We're a little more discriminating than that. Sophisticated. I forgot my monocle. This is like when I should put in the monocle, but it's like I don't have one. Okay, let's see the inductive case. Take a moment to scope the context, see how you feel about it. Let's see what we know. Okay, double s of n prime is equal to double m. Okay, we don't know anything about m. We're probably going to have to do some case analysis. Maybe you see that in the tactics. Cool. RAH says if double n prime equals double m, then n prime equals m. Okay. Now we have to show s of n prime equals m. So, okay, let's just see what m is, and then we'll find out where we end up. Okay, so by cases on m, now, just as before, when we have a case mismatch where n is successor of something and m is not, right? We're in the inductive case and m is 0. Before we were in the base case and m was successor of something. We have this contradiction up here in eq. Now here the contradiction sort of flipped, right? Where and now we have here on the left, we have double s n prime is going to be successor of something, and double 0 here, that's going to be 0. So we can witness that by simplifying. Not witness in the sense of existentials, but witness in the sense of seeing. Okay, and at this point, we can say, okay, no way that's happening. Okay, let's look at the last case. All right, things are looking good. Let's do some forward reasoning so we can figure out more about n prime and m prime. So if we simplify an eq, okay, good. So that sort of like pushes the successors to the outside. We do an injection to get a new eq prime. Okay, double n prime equals double m prime. So now we should be able to apply our IH and we're made. But what? We know that double n prime is equal to double m prime, but our IH will only apply, the precondition, the thing to the left of the arrow here, will only apply if double n prime is equal to double s of m prime. But like, look, you can't have this fact and this fact at the same time, right? Like, not for the double we defined. So we're stuck, right? It won't unify, right? If you try that, right, you'll see that it sort of explains like, yeah, you've got this mismatch here. These don't match, right? So there's this extra s in the way, right? What happened? So what happened is when we said induction here, the moment when you say induction fixes things in the world, right? So we're now doing induction for some particular m and this particular equality. And that's why when we get here, you can actually see the seeds of our own destruction were already sown by the time we got to the inductive case, right? This is double n prime equals double m. But like really we want that, this is for the original m. We want this to be for m prime so that our IH is useful at all. What do? We need to do what's called varying the induction hypothesis or generalizing the induction hypothesis. we need to be a little more careful about how we do induction. Let me show you. It's a tiny change. Oh, excuse me. Right, that doesn't work. It's a tiny change. Let's get into the let's redo it. We're gonna get it. We're gonna get it right this time. I promise. Okay. So all I've done is introduce n, and now notice the proposition that I'm proving leaves m fully quantified, universally quantified. We're saying this for any m. I'm gonna do induction now, and again, I've apparently forgotten to write the IH. Okay, so now it's just going to kind of go through. So the base case, it turns out, can be basically the same. Well, now we owe an intros, right? Like we're short at intros, so like okay, we have to put it in there because we never introduced it. So in the base case, because it didn't introduce m and eq, we have to do it now. Other than that, you can compare in your own file. The tactics here are identical. Right, so just as when you move from destruct to induction, your base cases don't change. When you move from a plain inductive hypothesis to a varied or general inductive hypothesis, your base case will remain largely the same. You might have to do some intros just to keep up with things. Okay, great. Now let's look at what the story is here. So let's see what we have. Our IH is almost exactly what it was, except for this one new part. Because we hadn't introduced m, this is still universally quantified. It's for any m. So you might look at this part here and be worried, saying like, well, that m, it's still a fixed m, but it's not fixed, right? This is any m. It just happened to have the name. Now our goal is for any m, double Sn prime equals double m implies Sn prime equals m. We can introduce all this. I'm going to simplify here just to make things a little simpler, though, just as well. Okay, so now let's go through with our original plan. We'll go by cases on m. Right, the case where m is equal to 0, we get the same issue, right, that we saw before. Okay, now let's look at what we got. Simplify our equality. Right, so let's see what we have. Our AH says for any m, if double n prime equals double m, then n prime is equal to that m, whatever m we chose. Our equality eq says successor of double n prime is equal to successor of double m prime. So injection will strip away those two matched pairs of successors. Okay, now we can do more forward reasoning. IHN prime should now apply here, where we're going to instantiate this universally quantified m with m prime. You see how that unifies, right? This bit unifies here. This bit unifies here. Okay, so we apply it. Beautiful. We know n prime equals m prime. We can rewrite reflexivity, and we are made. Okay. So you need to be careful. If you get it stuck with an IH that's too specific, you have over-introduced and you need a more general IH. Most of the rest of this file is going to be talking about techniques for doing that and identifying circumstances where you need to do that. So I'm going to take a pause here. In the next video, I'm going to do another theorem, and then we'll move on and talk about this in a bit more detail. Talk to you soon.